Good afternoon, everyone. My name is Kathryn Hinkelman. I am a PhD student at the University of Colorado Boulder and a member of the Sustainable Buildings and Societies Laboratory. Thanks for coming to the talk today. I'm here to present our work that we did in collaboration with Virginia Tech on a modeling framework to evaluate energy, transportation, and communication interdependence in smart and connected communities. For the agenda, I first am going to introduce the motivation for this project and present our vision for future smart and connected communities. Then I will present the models that we developed in Modelica to study the interconnections of energy, transportation, and communication systems on a community scale. The case study we implemented is a small theoretical case of a community in San Francisco. I'll present this case study as well as the results. Lastly, I will conclude the talk with a summary of the project and leave you with our future work. Before I get started, I want to first mention that these models have been open source released and are freely available for anyone who is interested. You can access them from our laboratory's website with the URL that's listed here at the bottom of the page. So what is the challenge we're trying to address? Both climate change and urbanization are two megatrends that are causing some serious stress in our legacy infrastructure systems. The energy, communication, and transportation systems are three critical infrastructure systems that are being really pressurized due to both climate change and urbanization. Some of the ways that these challenges are manifesting themselves are in the energy sector, both global warming and power outages, for example. In communication, there's communication congestion and packet losses. And in transportation system, we're seeing road congestion and poor local air quality. And these are all some big challenges that we're trying to see through with our societies. And as we look for more sustainable and resilient futures, these are some big challenges that we need to keep addressing. So that's the main focus of this work. And with those challenges in mind, this is what we have as our picture for a future smart and connected community. We envision a community that is smart, connected, and sustainable. And each of these three infrastructure systems allow this future to be possible. So in our vision, we have an energy network that has 100% renewable energy supplied from solar, from wind, from hydro, from geothermal. There's also battery storage in order to deal with the intermittent nature of solar and wind and these renewable sources. So we have lakes and hydro, and we have battery storage, and the buildings themselves actually can act as storage for thermal resources. The buildings also participate in grid services through demand response, for example. On the transportation system, we have a full fleet of autonomous electric vehicles to provide clean energy while providing the transport services needed for a community. Among these two infrastructure systems, we also have a communication system that enables the coordination and the complex dynamics of communication that's required for both transit and power services. So you can see here, this picture is fairly complex, and as we look at future smart and connected communities, this is still even maybe a simple picture of the true complexity of systems. So in order to understand this problem, we're trying to dissect these layers and pull apart the separate systems and understand their interconnections in a way that we can study them through a modeling framework. So for our modeling framework, we have proposed a 3M approach. That is the multi-layer, multi-block, multi-agent approach. At the top layer, we have a city layer. And if we go down, we have a block layer, and thirdly, an agent layer. So looking at the top layer, this city has multiple blocks composing of residential blocks, commercial blocks, and each of these are interconnected based with the vehicle roads, the communication transmission lines, and the power lines. Going down a layer to the block layer, each block has the three respective infrastructure systems. So here we see the communication system, the energy system, and the transportation system. And there's a lot of details that happen within these blocks, but then also there are the interconnections that occur between each of the blocks, so you can see at this layer. Down to the bottom layer, this is where we have each of the components in the infrastructure systems. So on the energy side, we have the renewable energy sources such as PV or wind. We have the distribution network, we have storage, we have the building loads, and the power consumption from communication towers. And you can see here there's lots of interplay among these components within each system, but there's also this interplay between system boundaries as well. So for example, between transportation and energy, you have electric vehicles that obviously require power in order to charge when the time comes. But at the same time, the user's driving patterns and charging patterns will affect the charging demand for the energy system. And if there's a variable pricing scheme, it might also affect the price and control signals for the energy side as well. So these interconnections are really the main focus of this work. We're still modeling within each system as well, but trying to understand the physical, cyber, and logical connections in order to understand how these different systems affect the operation of each other. So looking at the models we developed, this example here is an energy network model that includes both the residential district and the commercial district. If we unpack the residential district block, we can see here there's supply, there's demand, there's batteries, there's a transmission lines interconnecting each of these components. For the demand side, we can model a simple load model that includes the building load profiles, the EV charging, and the communication towers. Then depending on the use case for this system model, we can also look at a detailed model for the power side. This here is the IEEE 16-node test feeder, for example. Similarly, we can also drag and drop and change this block from theoretical systems to a real-world system model. And this is one that we've done with the historic Green Village, which is a real net zero energy community in Florida. Here for the transportation system, we have roads that are interconnecting each of the residential and commercial blocks. We also have EV charging stations at each block. If we unpack the road model, what we're doing here is we're calculating the traffic outflow rate based off of the road profile and the traffic inflow profile. The travel time model we used is an empirical flow velocity correlation that looks at the average road velocity, the average vehicle flow, based off of the length of the road and the capacity of the road. For the EV charging station, we did a simplified probabilistic model that looks at the change in the number of vehicles at each block based off of the inflow and outflow rates of the vehicles. In the communication system, we have both the transmission lines and the cell towers. In this model, we grabbed a packet loss model from literature that represents the packet loss rate as proportional to the normalized throughput and the transmission threshold. Validation, we compared many of our component models with several literature sources. For example, here on the power distribution side, we compared with this source here, and you can see for the IEEE 16-node test feeder, the bus voltage matched the original data fairly well, within 2% relative error for all locations. For the road model, we looked at this literature source here that was an experimental study where they measured the traffic inflow and outflow on a real road for 6 hours. And you can see here that our simulation data matched literature very well. For a case study, we modeled a theoretical community in San Francisco. This community consists of 2 residential blocks and 1 commercial block. And to study the interconnections of the 3 infrastructure systems, we looked at 3 different cases. First, with just the energy system alone. Second, we modeled the energy and transportation systems. And for third, we modeled the energy, transportation, and communication systems. For the transportation system, for example, we assumed that the fleet was entirely unmanned electric vehicles, and these vehicles were distributed throughout the 2 residential blocks and the commercial block. And on the energy system, for example, we included a grid connection assumption. We had PV arrays, a wind farm, electrical batteries. And for the load profiles of buildings, we assumed load profiles on an hourly basis from the DOE prototypical building models. This here is a picture of our 3 coupled systems model in Modelica. At the top layer, we have 2 residential blocks and a commercial block. And these are all interconnected by the roads, the power lines, and the transmission lines. If we unpack one of the blocks, we can see here we have the energy, communication, and transportation infrastructure systems. For performance indicators, we conducted a literature review in order to understand both the operational and safety factors for each of these infrastructure systems. Some we've listed here for reference. On the energy side, we looked at the peak value load ratio, the load cover factor. For transportation, we looked at travel time, traffic flow, and in the communication system, we looked at the packet loss rate and arrival rate. For one more specific example, I've listed here the bus safety indicator, which is a voltage limit placed by the IEEE standard 519. And what this looks at is it sums up over the total number of buses and the events, every instance where the voltage exceeds a 5% threshold in order to add to the indication. For results, here's the impact on the energy network. So again, we modeled each of the 3 cases. 1 is just the energy, 2 has energy and transportation, and 3 has all 3 coupled systems. And you can see in general here, this is a typical duck curve that is often seen with a high amount of renewable energy and high amount of solar in particular on an electric network. So for during most of the hours, there wasn't much deviation between the 3 different cases. However, during the peak commuting hours, both around 8 a.m. and 8 p.m., is where we saw some deviation occur from the power draw from the grid. And what you can tell here is actually when we added the transportation and communication systems in, the power draw actually decreased during these hours. And the reason for this is primarily because the electric vehicles were on the roads during the commutes, so inevitably there was less power from the grid since they were not at the charging stations. If we look at the transportation network, we can see here in the morning we have the morning commute, and here we have the evening commute. And between the red and the blue lines is essentially we're adding in the considerations of the communication system and the impact on the average velocity on the road. So when we added in the communication system, the average velocity actually decreased during each of these time periods. So indicating that there was higher congestion when the communication network was considered in the whole entire framework. And the reason for this, again, is we assumed that there was unmanned electric vehicles, so there's a lot of data needs with navigation and obstacle avoidance with the vehicles. And all this data caused some latency in the communication system and slowed down the car's abilities to drive effectively on the roads. Looking the other direction, here you can see the impact of considering the energy and transportation systems on the communication system. So during the morning commute and evening commute, what we saw was the packet loss actually surged during these times. And the reason for this was as there was more congestion and vehicle flow on those roads, with autonomous vehicles, there was additional need for coordination among the vehicles for effective transit. And this caused extra congestion on the communication lines and more packet losses on those lines as well. In conclusion, we developed a multi-domain modeling framework that we implemented in Modelica to integrate energy, transportation, and communication systems for future smart and connected communities. We open source released our library on our public lab website, which can be seen here. And the 3 case studies we implemented demonstrate the applications of the modeling framework for studying the operation of future connected communities. As future work, we are looking to extend this framework with discipline-specific tools through standard interfaces such as FMI. And we also hope to target specific use cases for SCCs such as dynamic modeling and optimization, resiliency analysis, and integrated decision-making. Thank you for your time and attention. and I look forward to the discussion and questions you may have during the Q&A.